Okay guys, in this video I was going to discuss single point energy calculations. So I'm just going to present a few slides describing single point energy calculations, and then what I'll do is I'll record another video where I go through an example of setting up a single point energy calculation using Gauss view, and then I'll probably make another video or I'll show you in class how to set up a single point energy calculation using the WebMO browser interface. So single point energy calculations are just what they say they are. The point in the single point energy calculation refers to a single molecular geometry. So one of the concepts that we're going to be studying in detail in this course is that the total energy of a molecule is actually a function of the molecular geometry. That is, as the nuclei move relative to one another, the energy of the molecule changes. And if you were to scan the energy of the molecule as a function of the molecular geometry, you can build a type of map, if you will, that we call the potential energy surface. That allows you to look at how the energy changes as, for example, a bond stretches or you rotate the molecule about a single bond, for example, a carbon-carbon bond rotation. And you can also perform such scans over multiple coordinates if you like. And so the single point energy calculation refers to the energy being calculated at one given molecular geometry. So not scanning the molecular coordinates, but calculating the energy for one geometry. And in Gaussian, these types of calculations are referred to by the acronym SP, so single point energy calculations. The energy that's calculated is the sum of the electronic energy of the system and the nuclear repulsion energy. Okay, so if you have fixed nuclear positions, right, the nuclei are all positively charged. There's a repulsive force at work between positive charges, and so that energy is included within the total energy. What is excluded from this total energy calculation is the thermal energy that would be associated with the motion of the nuclei, right? So because the nuclei are fixed, we're not addressing this thermal energy that would correspond to the motion of the nuclei relative to one another. You have to do different calculations to address that type of energy, and we'll explore those later in the course as well. In addition to calculating the total energy in these single point energy calculations, you also are calculating a representation of the many electron wave function. And that's usually described, at least in the types of calculations that we're going to be doing, in terms of what are referred to as molecular orbitals, which each have their own energy. And so these are somewhat analogous to atomic orbitals in the sense that they are a wave function that can accommodate up to two electrons, a spin up electron and a spin down electron, just as you learned about in general chemistry when you were exploring the Pauli exclusion principle and the quantum numbers for atomic orbitals. Now, the molecular orbitals are different in character compared to the atomic orbitals. In fact, the molecular orbitals are given as a superposition or a sum over the atomic basis functions in your basis set. And so we'll talk about that aspect of it in more detail as we proceed through the course. But for now, the take-home message is that both the energy and the electronic wave function for the many electron system are calculated in these single point energy calculations. And once you know what the molecular orbitals of the molecule are, you can calculate additional properties such as the dipole moment of the molecule, as well as higher order multiple moments such as the quadrupole moment and beyond that as well. And then from the molecular orbitals, the occupied molecular orbitals, that is the ones that are populated with electrons, you can calculate the charge density for the molecule and also the electrostatic potential associated with that charge density. And so we'll look at some examples of that when we do the practice calculations. For now, what I wanted to go over was how do you set up a single point energy calculation? What are the types of things that you have to specify in order to run the single point energy calculation? Well, first, you have to choose a model chemistry for your molecule. And the model chemistry that we're going to be using for many of our calculations is based on a density functional theory type of calculation. And this acronym right here, the APFD, the first three letters are the letters of the authors of this method, the letters from their name. So these are the last names of the people who authored this method. And then the D stands for dispersion. So this is a DFT type of approach. And then this particular flavor of DFT is called the APFD method. After the slash comes the basis set, and so this is a triple zeta basis set. It includes diffuse functions on our heavy atoms, and it includes these polarization functions. It includes an extra set of 2d orbitals on each of our heavy atoms, and it includes additional p orbitals on our hydrogen atoms. After the model chemistry is specified, one usually includes a job title that describes the calculation, and you can include as little or as much information as you want there. It's usually a good idea to document what the job is and why you're doing it. That way, when you go and look at the results sometime later, you have a sense of what you were trying to accomplish. You also need to specify the charge on the molecular system that you're studying. So if you're studying a neutral molecule, you would enter a charge of 0. If you're studying an anion, it might be -1 or -2, or a cation, +1 or +2, or whatever charge it is that you are studying. And then finally, well, not finally, but there's another property or another specification that needs to be input, the spin multiplicity of the electronic state of interest. And so I need to kind of qualify what that means. You'll recall, as I just mentioned, that you can have, that electrons have a spin. They're spin up and spin down. And what the spin multiplicity refers to is the number of ways in which the total spin angular momentum of the molecule can be oriented in space. Okay? In quantum mechanics, the electron's spin is quantized, and when you have a bunch of electrons together, the total spin of the molecule is also quantized. And so this is the number of ways in which you can arrange that particular spin, given the different arrangements of the electrons. And so the way to calculate the spin multiplicity is to take the number of unpaired electrons in your system and add the number 1 to it. So for example, if you're studying a 1-electron system, like the hydrogen atom, you have 1 unpaired electron, the spin multiplicity would be 2, and we would call that a doublet. If you had a molecule like methane, which has, in its ground state, has no unpaired electrons, that is, each spin up electron is paired with the spin down electron, then the number of unpaired electrons is 0, and the spin multiplicity would be 1, and we call that a singlet. If you were to take methane and promote one of the electrons such that you have 2 unpaired electrons, then the spin multiplicity would be 3, and you would be trying to find the triplet electronic state. And so that's how the spin multiplicity works, and we'll explore that through examples as we go throughout the course. So we'll have opportunities to mess around with the spin multiplicity for different systems and take a look at what the effect is. The point is that the spin multiplicity determines what electronic state you're trying to find. Ordinarily, in a single point energy calculation, but not always, you're trying to find the ground electronic state. And so, are all of the spins paired in your molecule, or are there unpaired spins? You actually don't know until you do the calculations. in general, you wouldn't know. Now, for simple systems, we know that this, the common knowledge tells us that the spins are paired or that they're unpaired. But in general, you wouldn't know that in advance, and you might have to study what should be the spin multiplicity for the ground state of the system. So you'd have to do multiple calculations to figure out which state is the ground state. The last little bit of information here, the minimum input that's required, is the geometry of the molecule. So you have to explicitly specify the positions of all of the nuclei, or you have to read them from a file. Luckily, the graphical user interfaces that we're going to be using assist us in building the molecule so that we don't have to do a bunch of calculations just to set up the geometry of the molecule that we're interested in. But in the old days, you'd have to do all of that stuff by hand. Here is going to be an example of an input file for a simple molecule. It looks like this is diatomic H2. And so Gaussian input files have the file extension .gjf or the file extension .com, stands for command. So these are the types of file extensions that are generated by the graphical user interfaces that we'll use. And I just wanted to show you what the different sections are, and we'll go through some additional examples as you start learning how to build your own molecules and set up your own jobs. So the first section here is called the link 0 section. Okay, and so that would be this first line here with the percent sign. That corresponds to a link 0 command. And in this particular case, there's only one link 0 command, but in general, you could have more link 0 commands. And what these do is they control the job resources, that is, what resources the program will use during the calculation and what files are used. And so we really won't need to mess with that too much. We may need to every once in a while. If you want to do really high performance calculations, it can often be useful to play around with these types of commands to make the jobs run more efficiently or to use more memory or less memory, that kind of thing. You may also want to do tricky things with the output and redirect the output in different ways, and so that's when those types of files can be, those types of commands can be useful. The next section here is called the route section, and you'll see that it starts with a pound sign. Okay, so what the route section does is it specifies keywords that control the type of job you're doing and the model chemistry that's being used. By default, Gaussian will always do a single point energy calculation, so you don't actually have to specify SP. However, you could specify SP and it would do the same thing. Here I've just left it off, and so Gaussian is going to automatically say, oh, he wants to do a single point energy calculation. Then what you see here, this is the model chemistry. So this keyword right here tells the Gaussian that I want to do a Hartree-Fock calculation, and I'm going to use the 321G basis set. Okay? And then there's a whole bunch of other keywords that you can include to modify what the program does. And we'll play around with those, and as I said earlier, the graphical user interface really helps a lot in the sense that it provides menus for activating different keywords. Okay, so we'll look at that more specifically when we do the video where we go through a Gauss view example. Here is an example of one keyword, the geometry keyword with its option set equal to connectivity. That refers to the format of the input file. It tells Gaussian to expect a connectivity section after the molecule has been specified. And in this job, it's not particularly important. You could really take this out and remove this section from the bottom of the input file, and the job would run just fine. But by default, Gauss View will add this section in. And so in a sense, it's related to how you build the molecule. The route section can encompass multiple lines. Once the route section is completed, it needs to be followed by a blank line. Then comes the title of the job. Okay, so here I'm just putting this as a simple title. My first single point energy calculation, and then the title. It can also encompass multiple lines. It needs to be terminated by a blank line. So next, after the title, you should have a blank line. Then comes the molecule specification section. The 0 here, this refers to the charge of the molecule, a charge of 0 in this case. So this is going to be a neutral molecule. And the spin multiplicity is given right here. In this case, it's a singlet. So all of the electrons, Gaussian will try to pair them up. Next comes the molecular geometry. The first atom is hydrogen, followed by the 3 Cartesian coordinates in units of angstroms. So we have a hydrogen atom that we see is oriented, or it's placed along the z-axis. Its x-coordinate is 0, its y-coordinate is 0, and it's 0.3 angstroms from the origin along the z-axis. The next hydrogen is also along the z-axis, and we see that it's placed at minus 0.3 angstroms from the origin. So here we've got a diatomic hydrogen atom that's oriented along the z-axis. One hydrogen has a z-value of 0.3, the other one has a z-value of minus 0.3. The geometry input is then terminated with a blank line, and then Gauss view automatically usually includes by default, it includes the connectivity section. Here, this is saying that atom 1 is connected to atom 2 with the single bond, and then atom 2 is also present. And then this connectivity section is also terminated with a blank line. Okay, so this is a very simple input file for doing a very straightforward, uncomplicated calculation using the Hartree-Fock level of theory with a rather small basis set. So this calculation on modern desktop computers will go very quickly. It won't take much effort at all. Next, I wanted to talk a little bit, or I just wanted to at least identify the types of output files that are generated by Gaussian. The .log file is a human-readable text file that contains information about the job status. That is, as the job is going, Gaussian will output human-readable information to the log file, and then it's also going to contain all sorts of different results depending upon what job keywords you specified in it. And so the log file is something that you might need to read from time to time, and Gauss View can open up a log file, and then you can use Gauss View to read different parts of the log file and do different subsequent calculations using the data that's in the log file. The .chk file is called the checkpoint file. It's a non-human readable file in binary format that Gaussian uses to store information about the calculation. The reason it's called the checkpoint file is because you can use that file to restart the job from where it left off. Very often, computational chemistry calculations are interrupted for whatever reason, and you may want to restart the job, but you don't want to restart it from the beginning. You want to start it from the point that you left off to save time. And that's the idea behind the checkpoint file. The fchk file is a text formatted version of the checkpoint file that is human readable, and it'll contain a lot of numbers in it typically, but basically you can convert a checkpoint file into a formatted checkpoint file, or you can convert a formatted checkpoint file into a checkpoint file using one of Gaussian's utility routines. And they tend to be more useful for the formatted checkpoint file for advanced work. We probably won't need them too much in our class, but you never know. It just depends on what you guys want to do for your projects. The next type of file, the .cub, is called a cube file, and it's a text file, so you can read it, but it's mostly just data. And that type of file is used for visualizing different types of quantities. Most frequently, it's used for visualizing molecular orbitals. So, for example, when we start using Gauss View to construct the molecular orbitals that have been calculated, that is to visualize them. You can save the result into a file called a cube file, and then you can just open that up with GaussU directly later on, and it'll save you some time. Okay, so this is a type of output file that you would often prepare yourself, containing the molecular orbitals or the charge density or the electrostatic potential. Anything that you can visualize three-dimensionally is stored in a cube file. And we're going to play around with that because that's part of the fun aspect of computational chemistry is doing the visualizations. These other files, these are usually they're temporary files, so usually they're not saved at all. The RWF file, it's very similar to a checkpoint file. The name read-write file, this is a type of file that Gaussian will dump information to, and it may need to read it back. It just depends on the nature of the job. It contains useful information. It contains typically information that goes beyond the checkpoint file. So sometimes it's useful to keep that information, but really that would be for kind of advanced work. Likewise, the .int file, it's a type of temporary file where Gaussian stores different values that it uses as part of its calculations. And so you typically don't need it unless you want to do some calculations that Gaussian isn't yet programmed to do. Maybe you're trying to design a new method or something like that. Then in that case you might save the integrals that are calculated, and then you can work with those to develop your method. So we will be using most frequently the .log file, the .check file, maybe the .fchk file, and then we're going to use .cube files. A little bit about the types of results that you can get. Before we go through an explicit example, I just wanted to talk about some of the important features of energy calculations. And so when you look at the output for your single point energy calculation, it's going to report a total energy value for the molecule. It's going to include the electronic energy plus the energy associated with the nuclear repulsion, and it's going to report that in units of Hartrees, right? That's the atomic unit of energy. 1 Hartree is equivalent to about 2,600 kilojoules per mole, or 27.21 electron volts. This value here is a typical energy that you might get out of a Gaussian calculation. Note that it is negative, and so that's going to be common. The energies are going to be negative, which means that the electrons are bound to the molecule. The first few digits are really dependent upon the size of the system. So if you're studying a very small molecule, you're going to get a small number here. If you're studying a very large molecule, you're going to get a very big number here. The real important details, for example, when you're comparing, let's say, two single point energy calculations for different geometries, the real important details are in the decimal digits. Okay, so the first couple of digits here, these numbers are on par with the nuclear geometry. That is, the 0.1 column and the 0.01 column here in the number. You're going to see differences in different calculations depending upon the arrangement of the nuclei. So that's a very big effect. Okay, so imagine taking, or you can do this with a calculator. Just take this number here, this 2625, and multiply it by 0.01. Okay, so that's going to give you something like 26.25. Actually, you don't need a calculator for it. 26.25 kilojoules per mole. So as the molecule, as the nuclei move relative to one another, you're going to see differences in energy on the order of 26 to 260 kilojoules per mole. Okay, so that's the energy range for which the nuclei are moving around relative to one another. Okay, so that's a large effect. The next two digits here, these are due to differences in the electronic structure. And so, so this might have to do with if you were, for example, taking a one molecule with a particular geometry, and you're trying to choose what is the best method to use, you would look at these two digits here to see which one gives a lower value of the energy. Okay, and so that's going to tell you something about the quality of the electronic state that has been calculated. The last digits here and digits beyond that, excuse me, these two digits here, these are below what we call the level of chemical accuracy. So numbers on these decimal levels really aren't relevant to chemistry. That is, there's no experiments that you can do in chemistry to really access those numbers. Now, there might be spectroscopic experiments where those are relevant, but not not for thermochemistry experiments and things like that. And then beyond that, the numbers, the digits are really just numerical noise. And so those numbers will be different depending upon what computer you're running on and at what time of day you're running the computer on. So the main important numbers, other than, the negative sign and the important digits are these first four. So you've got nuclear effects are encapsulated in the first two digits, and then the next two digits represent the electronic effects of the calculation. Okay, here's some rules. These are important rules. Okay, it's important that you use the energy that you calculated properly, because there are things you can do and things you cannot do. One thing you cannot do is compare the absolute energies for different chemical systems. Okay, and that has to do with the numbers out in front. Okay, these numbers are going to vary wildly for different molecules. So as I said before, a small molecule is going to give you a small value here, and a large molecule is going to give you a large value. So there's no use in comparing one energy to the energy for one molecule to the energy of another molecule. Now, that's one exception to that are isomers. So you can compare isomers because they have the same number and type of atoms, and they have the same number of electrons. You can, however, compare energy differences for different systems using the same model chemistry. So that is, let's suppose that I wanted to study the ionization energy of a molecule. I could calculate the ground state energy of one molecule. I could calculate the ground state energy of that molecule's cation and take the difference. That would give me the ionization energy for that molecule. And then I could do the same thing on a different molecule. Okay, and that's going to give me two energy differences. I'll have the ionization energy for one molecule and the ionization energy for a different molecule. Now, as long as I've used the exact same model chemistry for all four of those calculations, then I can compare the energy differences. Okay, so you can't compare absolute energies for different systems. You can, however, compare energy differences for different systems, provided that you use the same model chemistry. It wouldn't make sense to use a high accuracy model for one molecule and then a low accuracy model for a different molecule and then try to compare those numbers, because the comparison would be nonsense. Okay, so you have to be careful about what you do compare and what you don't compare. You can compare energy differences for different models provided you do them on exactly the same system. Okay, so if you're trying to figure out, which model is better for this particular system, you can make comparisons for the same system. Okay, and that's very commonly done. Let's see. These types of issues are articulated in the first two examples. I believe I'm going to be doing example 2.1 for you in the next video, just to illustrate how to set up single point energy calculations. Just a couple words on the properties that we'll be calculating. A property of interest is the dipole moment of the molecule. You have a sense of what the dipole moment is already. Is the molecule polar or is it nonpolar? Does it have a dipole moment or not? We can think of the dipole moment as an asymmetry in the molecular charge distribution. And its formal definition is the derivative of the total energy with respect to an applied electric field, and it's usually reported in units of dBi. And so this is I don't think this is the SI unit for the dipole moment, but it's one that's often used for reporting dipole moments. It's a convenient unit to use in that regard. It is a vector quantity. That is the dipole moment, which is represented by the symbol mu. It has an x component, a y component, and a z component. And so the x component is the derivative of the total energy with respect to the electric field applied in the x direction. The y component is the derivative with respect to the y direction, and the z component is the derivative of the energy with respect to the z component of the applied electric field. Another way of thinking about the dipole moment is as follows. So you have a number of nuclei in the molecule. That gives you a distribution of positive charge, right? Depending on where these atoms are located, where the nuclei are located, that's the distribution of positive charge. And there is a center of positive charge, just like there's a center of mass or a center of gravity for a material object. For charged objects, or for objects consisting of multiple point charges, there's a center of charge as well, center of positive charge for the nuclei. There's also an electronic charge distribution, right? Negative charge that's distributed throughout the molecule. And there is a center of negative charge as well. If the center of negative charge and the center of positive charge coincide at the same point in space, then you have a nonpolar molecule, and the dipole moment would be 0. If the center of positive charge and the center of negative charge are not at the same point in space, then you're going to have a dipole moment. And the dipole moment points from the center. It depends on your definition. I believe it usually points from the center of positive charge to the center of negative charge, at least in our general chemistry textbooks. Gaussian, however, flips that around, and the dipole moment points from the center of negative charge to the center of positive charge. So the dipole moments that you calculate may look reversed compared to what you would expect from general chemistry type of thinking. Nevertheless, it's the same quantity, and it can be calculated from the single point energy calculation. You can also calculate higher order multiple moments, such as the quadrupole of a molecule, and it tells you something about the shape of the charge distribution. And it's also described by a tensor, or this matrix here, right? This 3x3 matrix. The different elements of the matrix correspond to different derivatives of the energy with respect to the applied electric field. So this XX component would be the second derivative of the energy with respect to the X component of the electric field. The YY component here is the second derivative of the total energy with respect to the Y component of the electric field, and you have the same thing here for the Z component of the electric field. These mixed terms here, the XY terms, this would be the mixed derivative of the total energy with respect to the X and the Y component of the electric field. And you have the same thing here for the XZ and the YZ. Okay, and so this is related, the fact that there's multiple, there's now 9 derivatives here, this has to do with multivariable calculus, essentially. These are all first derivatives, whereas these would be multiple derivatives and their double derivatives, I should say, and their mixed derivatives. A couple words on the molecular orbitals that we'll be looking at. So the molecular orbitals are functions. They are linear combinations of the atomic basis functions that are used in the calculation. And by that I mean the molecular orbital is a sum of all of the atomic basis functions in the calculation, and each of those atomic basis functions are multiplied by a coefficient called the molecular orbital coefficients. And what the single point energy calculation does is it finds the set of molecular orbital energy, the molecular orbital coefficients that minimizes the total energy of the molecule. Okay? And then these different molecular orbitals are then occupied with electrons. We have both occupied and unoccupied molecular orbitals. The unoccupied molecular orbitals are often called virtual orbitals because there's no electron actually in them. And just some different features of them that we're going to be exploring through the examples. There's a particular molecular orbital will be the so-called highest occupied molecular orbital. That is, it's going to be the molecular orbital that has an electron in it that has the highest energy. So like the Pauli principle for atomic orbitals, it also applies to molecular orbitals. You add electrons to each molecular orbital, 2 at a time, with an electron spin up and an electron spin down. The highest energy orbital that is occupied by electrons is called the HOMO. The next molecular orbital up that is unoccupied is called the LUMO. And the relevance of these two orbitals in particular is that oftentimes you can model the lowest energy electronic transition of a molecule in terms of the energy difference between the HOMO and the LUMO. That is, when you excite the molecule, often you can regard it as an excitation involving promoting an electron from the HOMO to the LUMO. And so the energy difference there would correspond to the energy of absorption required to make that transition. At least that's one approximation. Orbitals can be classified in different ways. So we'll be talking about bonding orbitals and anti-bonding orbitals. The bonding orbitals can be of sigma type or pi type, right? And so sigma type orbitals, they have a circular symmetry to them about the bond axis. Pi type orbitals have a reflection plane. They have a nodal plane passing through them. We're going to look at different pictures of them as we go. And then there's also anti-bonding type orbitals as well that have the same symmetries, but there'll be a node in between the two atoms. So for bonding molecular orbitals, electron density is shared between the two atoms involved in the bond. For the anti-bonding orbitals, you're going to find that there's a nodal plane, that is, that the molecular orbital goes to 0 in between the two atoms. There's also non-bonding orbitals for things like lone pair electrons and such. This is where the electronic density is primarily located on just one single atom. And we'll look at some examples of that. One caveat to molecular orbitals is that they are really just mathematical objects. They are not physical objects, and so you have to keep that in mind when viewing them. Now, they are useful to think about and to study as part of your calculations, but they're mathematical in nature, not physical in nature. Additional topics that are relevant, and so these are topics that you may want to look into for your mini project on this Getting Started chapter. We can look at atomic charge distributions using the population keyword within Gaussian. You can also look at you can think about closed shell versus open shell calculations. For closed, the term closed shell refers to calculations where the spins of the electron are restricted in the sense that each orbital is doubly occupied. This is for molecules that have an even number of electrons, so each spin is paired. We call that a closed shell calculation. If you have an odd number of electrons, or if you have a which would correspond to a radical, or if you have a biradical structure, you would then need to do what are referred to as open shell calculations. And so when you set up your job, you need to well, you often don't need to specify this, but you can specify closed shell versus open shell. So you can control whether or not the spins of the electrons are forced to be paired or whether you allow them to be unpaired. And these open shell calculations, they essentially treat the up electrons independently of the spin down electrons, and that can change the results just depending upon the system. And so we probably won't have to make that distinction too often ourselves. We'll be given some advice to do that in the example problems that we'll do. But when you go to start constructing your own project, we may need to think about that. We'll just have to take into account how many electrons you have in your system and whether or not closed shell is appropriate or whether open shell is necessary. I'll just point out that if you're going to study a radical, that is something with an unpaired electron or one of these biradical singlets, or if you're interested in studying how the potential energy associated with breaking a chemical bond, you need to be doing open shell calculations for that case, because the closed shell variation of calculations will not give you good results. Oh, there's a little example on bi-orthogonalized orbitals that you can look at. We're going to be doing a whole unit on optimization calculations and finding minima or maxima by seeing how the energy of the molecule changes as a function of the molecular geometry. Along with that, one often does a frequency calculation to verify that you found a minimum in the energy. These calculations can be also useful for studying vibrational spectra such as infrared and Raman, or if you're interested in the 0-point energy of the molecule and calculating various thermodynamic quantities, you need to do frequency calculations. And so there'll be a separate unit on frequency calculations as well. A more advanced topic that we may or may not get to, it just depends on what projects you want to do, would be onium calculations. This is where you have where you use layered calculations in the sense that you have a small portion of your molecule that you want to treat with a high accuracy method, and then the other parts of the molecule you will treat with lower accuracy methods. And so this is a strategy for studying rather large molecules efficiently. That is, in a short enough amount of time that you can get useful results. And so if you've got any big molecules, or let's say you're interested in, I don't know, some of these porphyrin molecules that Dr. Zhang's group may be studying, you're interested in the main porphyrin ring, but then like there's these long, these large bulky substituents attached to them. You may or may not be so concerned with treating those as accurately. You might treat those with the low-level method, but you want to treat the electronic structure of the porphyrin with a high accuracy method, or as high accuracy as you can afford. At least they're still pretty big calculations. In any case, so I'm going to go ahead and stop this video here, and in the next video I'm going to go through a single point energy calculation on formaldehyde.